Okay, now this time, well, let's talk about walk down. Okay, let's talk about walk down again. Now, I would like to consider this. We know walk down is force times distance. Okay, so this formula only works if the force is constant. Okay, only works if force is constant, is unchanged. Okay, for example, if I have a dog, let me use a dog. So say on the ground, okay. Now I have a box. Okay. Now I attach it to a dog. So I have a dog, something, something like this. Okay. Okay. So yeah, I have a dog. Now there's a dog. Now if a dog is pulling a box along, okay, and the force is of course is not, it's not constant. So what normally physicists do, they draw a diagram, okay, in terms of the distance and the force. Okay, so assume they move. Sorry, assume they move steadily. Well, I assume the dog is really nice, so the dog moves. The graph looks like that. Okay, the further away, sorry, the further away it moves, the more force it applies, okay, to the box. So so this time, okay, how do I find the work done? What is the work done by the dog on the box? Okay, so the answer is the answer to that, okay, is quite simple. It's actually just the area under the graph. Okay, now the area under the graph. So just remember the area under the graph. Okay, let me write it down. The area under the graph is the work done. Okay, the, sorry, the area under the force distance graph. So yep. So um, if you well, but we can prove it. Okay, so have a look at the unit of the area here. Okay, the unit of a force distance graph, okay, will be meters. Sorry, I made a mistake. Newtons times meter. Okay, a Newton meter is 1 Newton meter is basically 1 joules of energy. Okay, Newton meter. It will be something like that. Okay, so the idea is, let's talk about area under the graph. Okay, this time. Uh, um, Okay, now let's talk about the area under the graph. The area under the graph always means something. Okay, now let me do an example. If I have, say, so if I have a velocity time graph, the area under the graph, so if I have a velocity time graph, look like that. Okay, now, and I forgot what does the area under the graph mean. Okay, if whenever I forgot what it means, okay, look at the units. Okay, the area under the graph. So if you ever forget what does the area under the graph means, look at the units and times them together. Okay, meters per second times seconds. Okay, they cancel out. Okay, the unit will be meters. So the area under the graph, okay, means something meters. So it must be displacement or distance in this case. Okay, so also if you have a look at the gradient, okay, also the gradient of the graph means something. If you ever forgot what does the gradient mean, have a look at the unit. I have meters per second divided by the vertical divided by the horizontal. Okay, so I will have meters per second square, which is acceleration in this case. Okay, so yep. So if you know, okay, if you just you when so sorry in physics, if I give you a graph, okay, by looking at its units of x and y axis, you can actually calculate what does the the unit, what does the area under the graph means, or what does the gradient of the graph means, by simply just times them or divide by them. Okay, so this is a very useful technique. Okay, now let's start. Let me talk about the conservation of energy. Okay. Okay. Now, golden rule is, okay, the total energy would always be the same. Okay, I'll show you what I mean in here. So, the idea is, say if I drop a ball, okay, I have a ground. On the ground, okay, I drop a ball to the ground. Okay, initially, it has a velocity of 0. Okay, it does not have kinetic energy. Okay, most of its energy will be potential energy. Then, if the ball, okay, drops halfway there, okay, it will have a velocity of something. Okay, call it v1. So, since it drops down, okay, it's well. Let me write it down this way. Okay. Initially, the kinetic energy will be 0. Okay, all of it will be potential energy will be a lot. Okay, now at this point, okay, the potential energy because since the ball dropped down, the potential energy would decrease, okay? And since the ball moves at a speed, okay, the kinetic energy increases. Okay, this should make sense. Now, when the ball hits the ground, okay, impact with the ground, okay, the potential energy will be zero. Okay. However, the kinetic energy would increase because it moved faster. It traveled faster. So, so what we can analyze is if I lost. So, have a look. Okay, the potential energy has been lost. Okay, as a result, the potential energy has been converted to kinetic energy since it moved faster and faster, and so we call this the This is an example of the conservation of energy. Means the total energy, okay, the total energy will be the same, is the same, and it's always the same. Let me show you this. Okay, so again, now we have a skater, okay, and the giant comes here. So I'm the giant. I move it up. Okay, so as you can see on the right hand side, okay, the potential energy is a lot. Okay, so since I drop it, okay, now I do it again. Okay, when I drop it, the potential energy would decrease, and the kinetic energy would increase. Okay, and the total is the same. So if I put this guy on this on the track, you can see that. Okay, so at the highest point, it has more potential energy. It moved slower. Okay, so since it moves down, it has more kinetic energy and less potential energy. Okay, the total energy is the same, so its potential energy has been transformed to kinetic energy in order to increase its speed. Okay. So if you look at again, if you look at the right hand side bar, now if I stop it at the lowest point, okay, it has the most kinetic energy, okay, since it moves faster.